Darkwing Duck. When there's trouble, you call DW. Darkwing Duck. Okay, so what we're looking at here are transmission lines for current. So if you have a power plant, there's probably not a power plant in your backyard, right? Your power plant exists some distance away from you, probably miles. How do they get power from the power plant to your house? And the easy answer is like, well, it's electricity. It goes through the wires. It goes through the transmission lines. But like, have you ever wondered how they manage to get it through the transmission lines and how much electricity is actually there? Well, that's what we're going to take a look at here in this example. When this idea kind of like first came about, we first like started talking about circuits with direct current. This was a lot of Edison's ideas. We've got Ohm's law, V equals IR, and this is like a very straightforward method. We were able to do a ton of stuff with circuits this way. So let's just apply this idea on a larger scale. Okay. Now in America, and if you're in a different country and you're running like different electrical grids and stuff like that, this will be a little different. But in America, we actually have 3 bands of electricity coming into your house on the drop line. Generally speaking, like these are in different phases, but for whatever. Generally, your houses will at max need 240 volts. Okay. Electric stoves, electric dryers, fast charging stations for your cars, assuming this video is still here in the future. We're all driving electric vehicles around. 240 volts is like the high voltage you need in your house. Most things in your house will run off of 120 volts, but you need 240. Okay, you need 240 to be there. So if houses need 240, and let's say that your town is 10 kilometers away from your plant. So you're 10K away from your power plant. And let's just say that, let's just give a reasonable value for the resistance of the transmission lines. Let's say that 10 kilometers of transmission lines has a resistance of about 0.4 ohms. We can make those transmission lines like a little bit thicker. They're made out of like nice copper, so they're very low resistance. Let's just call it like 0.4 ohms. That's a very small amount, right? 0.4, that's very small. Okay, a 1 ohm resistor is more than that, and 1 ohm resistors is this big. So if I have an entire town, then my town needs, something like 120 kilowatts of electricity. Okay? So with each house needing 240 volts, 10K away, a resistance value of the lines, and my town needing 120 kilowatts of electricity at any given point in time, how can we do this? Okay? And if I'm a power company, I guess my real question is, how much power am I losing? Because if I need to send out electricity to the town, but I lose, 100% of it on the way, I haven't really sent anything. But if all of it gets there, then we're happy. So what is the actual amount that we're lost? How much power are we losing here? So let's think about this. If we want to think about how much power is lost, we could go and say, well, power equals a number of different things. In this case, we might want to say like, oh, power equals V squared over R, but we can't easily do that because we don't know the power that's lost over the wires themselves. That's not exactly helpful. What's a little bit more helpful in this scenario is to say PIV, P equals IV. Because if we say P equals IV, we know the power we need. We need 120 kilowatts in the town. That's the power we need right here. Remember, that's a power. Kilowatts is a measure of power. And I know the voltage that I need in each household. I know my voltage needs to be somewhere around 240 volts. So that's nice. So this allows me to just grab how much current is going through the wire to begin with. Okay? And if I have that current and the voltage and the resistance, I can like start rocking some other things and we can work from there. So let's just take a look at this. Okay? So if we want to find the current here, let's see. We can say current equals power over voltage. That is 1.2 times 10 to the 5th watts, that's 120 kilowatts, divided by our voltage, 240 volts. And when we do this, we see that the current running through our power lines is 500 amps. 500 amps of current. That's an insane amount of current. Bzzz, like beam it up. Now, if we wanted to look at the amount of power lost, well, we could do this. The power that is lost in the lines is the power that's lost like by the resistor. So if we wanted to do this, we could say, hey, look, the power lost in the resistor is equal to the current squared running through the line, that resistor, multiplied by the resistor itself. So this is going to be like 500 amps squared, and then a very, very small resistance. It like hardly even matters, 0.4 ohms. And if we multiply all this together, where's my calculadoro? Let's see, 500 squared times 0.4, that gives us, let's just do this, 2, a bunch of zeros. That should give us something like 100 kilowatts of power is lost. But we were only supplying 120. You're saying that we lost 100 kilowatts out of our 120? We lost 80%? That's ridiculous. That is a lot of power that we are just burning and just saying like, yeah, it's gone. We burned a bunch of coal and it did nothing. We burned a bunch of natural gas and it did nothing. We used a bunch of renewables and we lost a bunch of it. It's just gone. That's a bad thing. Okay? So, if I'm a power company, how can I prevent losing all of this electricity? Because if I could lose less of it, then I could sell more of it, and then woo, we're all happy. Well, if we go back and look at these equations, one of the issues is that this voltage here is too low. If I could up this voltage in the denominator, if I can make it a very large value, then what would happen is my current would go down, right? And if my current went down, then the power lost, the current squared times the resistance, this 100 kilowatts that we lost would go down as well. So I just need to up the voltage. I just need to say, hey, people, stop using 240 volts in your house, a reasonable amount. Let's use like 24,000 volts in your house. Because if I did this, then if we go through the same process again, the current I would have is 1.2 times 10 to the 5th watts divided by 24,000 volts. And in doing so, I'd only have a current of 5 amps. And then when I go and I lose that amount of power, so here's my power lost in the resistor, that's just going to be 5 amps squared times the 0.4. That's 25 times 0.4. That gives me something around 10 watts. That's nothing. That's not even a kilowatt, right? This is only something like 0.008%. It's like nothing. This is what I want. So everybody, just start using 24,000 volts for all your stuff. You'll be, wait a second. If you're using 25,000 volts or 24,000 volts in your house, this is A, dangerous, and B, we're going to blow up like a whole bunch of your circuits. I'm going to have like some serious things to kind of change this voltage amount because I don't want 24,000 volts through everything. So this is what the companies want, but that's a tough thing to build. So how can we do this? How can I get, as a power company, the ability to send out 24,000 volts or even higher, right? Like if I'm able to get this number stupidly big, if I can get this number to like 500,000 volts or even more, then my lost amount will be even less, which is amazing. But I need to keep your 240 volts in check. So power company people, we're going to have to move away from direct current to get this to happen. And we're going to have to implement something that we're going to see in our next video. So check that out, and then we will see what we've implemented to keep the power company happy and to keep you, the consumer, happy as well. But until then, adios. Take it easy.